In last lecture, we have seen the ideal properties of pumps. Now here in this lecture, we are going to see in detail about the pumps. So three types of pumps are there. We have seen in the last lecture. First is the reciprocating pump, second is the syringe pump, and third is the pneumatic pump. So first, reciprocating pump, or it is also called as hydraulic pump. So majorly two types of pumps are there. One is the hydraulic pump and another is the pneumatic pump. Hydraulic pump means the pump in which we are pressurizing anything with the help of liquid, and in the pneumatic pump we are pressurizing anything with the help of air pressure. So reciprocating pump is the hydraulic pump. It is 90% commercially available in the HPLC, or it is this type of pump is more popular in the HPLC. So as we are seeing in the diagram, faint blue color is there and dark blue color is there. So faint blue color is the small chamber in which inlet and outlet wall is there, and the dark blue color is showing with the piston. So here this reciprocating pump is consist of small chamber which is shown in with the faint blue color or navy, sky blue color. So this small chamber in which the solvent is pumped by back and forth motion of the motor driving piston. Here two ball check valves are there which open and close alternately to control the flow of solvent into and out of cylinder. The solvent is in direct contact with the piston. The pressure is transmitted to the solvent via a flexible diaphragm. So this piston is moving back and forth, and accordingly the check valves are opening and closing alternately to push the mobile phase. So this is the function of reciprocating pump. What are the advantage of this pump? It is the advantages, it is a constant flow rate we are getting, means continuous flow rate, not pulsating flow. Constant flow rate we are getting by using reciprocating pump. So here it is independent to the column back pressure, means column back pressure is not hampering the performance of this reciprocating pump, and solvent viscosity is also not hampering the function of this reciprocating pump. It gives a high output pressure up to the 10,000 psi, and here the small internal volume is there, 35 to 400 microliter. The disadvantages, it can produce the pulsating flow and cause baseline noise. So when we are passing the solvent, it can cause the pulsating flow we are getting, but constant flow we are getting. Okay, pulsating flow but constant, but this pulsating flow, this problem is also not much more, it is very small, tiny, so it is not a major issue with this pump. Then second is the displacement pump or syringe pump. It is like a syringe. So it consists of syringe like chamber which is equipped with the plunger, activated by a screw driven mechanism and powered by a stepping motor. The advantage of this pump or syringe pump is here the flow independent of viscosity and back pressure is there, and output is also pulse free. And disadvantage is it has having capacity up to the 250 ml, and it is inconvenient when we are changing the solvent. So this is the displacement pump. Last is the pneumatic pump. Here the pumping system is based on the air pressure. So this pneumatic pump is like a collapsible container or collapsible tube. This is the simplest pumping system in which the mobile phase present in the collapsible container housed in a vessel that can be pressurized by a compressed gas. The advantage of this pump is it is inexpensive and pulse free. Disadvantages, it has the limited capacity and pressure output and dependence of the flow rate on solvent viscosity and column back pressure. is not amenable to the gradient illusion and limited pressure of less than 2000 psi it maintains. So among all these three, the reciprocating pump is producing the high pressure and more advantage are there. So reciprocating pump is most widely available nowadays with the modern HPLCs. Then PreColumn, next part is PreColumn or saturated column. This PreColumn is used to prevent the analytical column. It is fitted between the pump and injector, which ensure phase is fully separated with the silicon or silicate ion prior to the injection. So this PreColumn is situated between the pump and injector. So this is helpful to ensure whether our stationary phase is fully saturated or not. So the another advantage of this is if we are using the pH more than 8 or less than 2, or the temperature of more than 50 degree, or if we are using the buffer, so this can cause the void at the top of column. So this is happening with the PreColumn. So we can prevent our analytical column, which is more costly than the PreColumn and guard column. So whatever the ill effects are there, this will happening with the PreColumn, and we can prevent our costly analytical column by use of PreColumn. So use of PreColumn reduce adverse effect of low and high pH mobile phase, and it ultimately it will increase the life of column. Then next is injector. Three types of injectors we are using: syringe injector, stop flow injection, and rheodyne injector. So what is happening with the syringe injector? In the syringe injector, injection through self-sealing elastomeric septum is there. We are passing our sample in the column or in the HPLC system through the self-sealing elastomeric septum. Here the micro syringe is used, which stands pressure up to the 1500 psi. So this is the syringe injection. Second is the stop flow injection, in which the flow of solvent is stopped and fitting of the column is removed, and after that sample injection into the head of the column takes place, and after fitting of column takes place and flow of injection starts. So what happens when we want to introduce our sample over here in the stop flow injections type? So we have to stop the system, we have to load our sample, and again we have to start our system. So this is very tedious and inaccurate process. Third is the sampling loop, that is here we are using the rheodyne injector. So nowadays with all the modern HPLC we are using the rheodyne injector. Here this is the diagram we are seeing over here. Here load position you are seeing in the diagram, and inject position you are seeing in the diagram. So in the load position, what happened, we have to load our sample into the system, and inject position we have to inject our sample into the system. In the load position, whatever the mobile phase is there, it is coming from pump and going to the column. But as we are injecting our sample, so the pump system is connected to the filled sample loop, means where our sample is get filled, it is connecting to the pump, and our sample is passing through the column. So this is the injection system. So this rheodyne injector, here it is made up of 6-port rheodyne valve in which samples fill an external loop. So in the first diagram, load position, whatever the C shape you are seeing of the loop, so this is the loop which is filled with the sample. Then after injecting our sample, we had to rotate the rheodyne injector clockwise. So whatever the sample is there, it is connected to the pump and inject through the column. So this is the function of the rheodyne injector. Now this is the diagram we are seeing of the column. in the diagram we are seeing the HPLC column also, in the rheodine injector also we are seeing over here. So these are used mostly nowadays in the modern HPLCs. Now we are going to see about the HPLC columns. So in this picture we are seeing the C18 column. Mostly C18 column, it has the it is most commonly used in the HPLC, and this having the diameter of 4.6, length 250 mm, and the particle size maintained in this column is 5 micrometer, and the pore size maintained is 300 angstrom of the stationary phase. So this is very accurately maintained in the HPLC. Now in the HPLC, three types of columns we are using: analytical column, semi-preparative column, and preparative column. So this analytical column is used for the separation of analyte, and C18 column is the example of analytical column. Preparative column is mostly used for the isolation of analyte. Here in the slide we are seeing that the particle size difference, column diameter, and sample loading. In the analytical column we are seeing that mostly 3 to 5 micron particle size with internal diameter from 0.3 to 4.6 millimeter, and we can load the sample from nanogram to microgram range. Means very small sample is required here for the separation of analyte. But here in the preparative column we are able to load more sample, that is in the gram scale. The particle size of the stationary phase is more, that is 10 to 30 micron, and the column diameter is ranging from 5 to 200 millimeter. So this is the column ID which is used.